Aside from dereferencing a pointer and maybe assigning it to a variable, the other thing you might want to do with a pointer is to do arithmetic. The addition and subtraction operators can both be used with a pointer operand such that, say, you can add a pointer to some integer, or you can subtract an integer from a pointer, or you can actually subtract one pointer from another. When you add an integer to a pointer or subtract an integer to a pointer, what you get back is a pointer representing the address of that offset. So here, for example, I have an int variable named I, and I have an int pointer variable named p, and so when I reference I get the pointer value representing the address of I, and then when I add 2 to that pointer value, what I get is an int pointer representing the address, which is 2 ints up in memory. And so assuming we're compiling for a platform on which an int is 4 bytes, that means we are assigning to p here a pointer representing the address which is 8 bytes above where I starts in memory, because 2 times 4 is 8. If instead we were subtracting 2, it would be the address 8 bytes below in memory. If we were adding or subtracting a char pointer here, well, char is only 1 byte in size, so say adding 2 to a char pointer produces the char pointer representing the address that's only 2 bytes above in memory. Or say if I were adding 3 to a double pointer, well, a double is 8 bytes in size, and 3 times 8 is 24, so it would return the pointer representing the address that's 24 bytes above in memory. So this in fact is the other reason why pointers are typed, because when we do arithmetic on a pointer, we want to know the size of the thing being pointed to. Now you're probably wondering here what use this is, because what we've produced here in P is a pointer that points to some place in memory we have no idea what's there. We have no reason to believe that there's an integer value 2 places up in memory from where I was declared. Well, in truth, you actually wouldn't use pointer arithmetic in this way. Pointer arithmetic is used when you have contiguous blocks of memory that you get by allocating it from the operating system or by creating what's called an array, which we'll discuss in a moment. Still, the compiler will not stop you from doing this, and in fact we can dereference P. What happens is that the bytes in memory starting at that address are treated as if they are an int, and that value is then going to be assigned here into I, but really you have no idea what to expect. The int value we get by dereferencing P here is basically just going to be garbage. It's going to be whatever happens to be in the bytes at that location. As I said in passing, you also can subtract one pointer value from another pointer. What you get back in that case, though, is not another pointer value, but rather an integer representing the distance between the 2 pointers. The distance, though, is not in bytes, but rather in the number of things of that type that fit in that space. So if you subtract one double pointer from another, you get the number of doubles that fit in that space between the 2 addresses. And this does mean that the 2 pointers must be of the same type, otherwise it wouldn't make any sense. What we cannot do is add one pointer to another, because the result would just be meaningless. If I have a pointer representing the address 100 and another pointer representing the address 300, adding them together to get a pointer representing the address 400 doesn't mean anything. There's just no way that could be useful. Normally when we deal with pointers, we have no idea what the actual numeric addresses pointed to are. This is because we get the pointers mainly by referencing variables, and it's up to the language to decide where to actually put these variables. As programmers, we really don't want to have to care about the precise address of every variable. However, there are some special circumstances under which you may want to have a pointer that points to a fixed address. So for instance, if you're writing a device driver or some component of an operating system, you may need to specify some precise address because there's something special about it. To get such a fixed address, we simply take an int literal and we cast it into a pointer. So here what we have is we are taking an int literal expressed in hex notation, as you can tell by the 0x that precedes it, and we cast it to an int pointer. So the variable p now holds an int pointer of the address B000FFFF. Understand that in a normal program, a program that's just meant to run as a process in an operating system, you very likely don't want to do this, because if you just come up with some arbitrary address, you don't know if your process even has access to that address. So in a normal program, if we try and dereference p here, it's quite possible that we might end up terminating our process with a seg fault or something. On some platforms, though, there may be ranges of addresses set aside within a process, which are used to talk directly to some hardware device, Like say there may be a range of addresses set aside representing the video frame buffer, and when you write to it, you write directly to the screen. But again, such addresses are platform specific. So in fact, in general, if you're using fixed addresses, your code instantly becomes really unportable. It's something you would only do when you're targeting one specific platform. Now, there actually is one integer value which is considered special, and that's 0, because you can assign 0 to a pointer without having to cast, because the address 0 is treated specially as effectively representing nothing. So in fact, a pointer with the value 0 is called a null pointer. Much like with numbers, a pointer value of anything other than 0, anything other than null, is considered to be true, but the pointer value 0 null is considered false. So here in this if, when we have the condition p, well, p is a null pointer, so it's going to test false. Finally, the last thing you can do with pointers is to use them in comparisons. So say you can compare two pointers to see if they are equal to each other or not equal, meaning do they have the same address. Or you can see if the address of one pointer is greater than or less than another pointer, or greater than and equal to or less than and equal to another pointer. And you can use the not operator, which returns the inverse truth value. So if the pointer is null, it returns 1, otherwise it returns 0. By weak typing, remember, we mean that we can violate the types of our data in memory. We can modify a value in memory using operations not defined for that data type. So for instance, say we have a float variable f and we assign it the value 98.6. If C were strongly typed, the only way we could modify f is if we were to use the operations defined for float values, namely arithmetic. Like say we could subtract 2 from f and then assign the result to f. With pointers, however, we can do something like this. Let's say we have a char pointer named p, and then we get the address of f with the reference operator, cast it to a char pointer, and then add 2. Effectively, we end up with a char pointer that points to the third byte within f. If we then assign a value to the dereference of p, we are effectively writing whatever arbitrary thing we want to the third byte within the float f. So f is getting modified, but not via one of the defined operations for floats. Hence we are violating its data type. This is weak typing. So C is a statically typed but weakly typed language. Pidgin, in contrast, was a dynamically typed but strongly typed language, because in Pidgin, if we attempted, say, to add a string to a dictionary, that's a nonsense operation that's not defined for those types. So that operation will not be permitted to go through. Now, it won't be caught at compile time because there's no static typing, but then at runtime, before the operation is performed, the language checks what the actual types are and it says, you can't do that with these types, so that causes an error and the program terminates. In C, in contrast, the language doesn't do any checks at runtime.